This video provides a quick recap of section 10.1, in which we introduced this new thing that we're going to analyze in chapter 10 called the sequence. Quick definition: a sequence is an ordered list of numbers, and we denote the specific terms of the sequence as a sub n. And here is referred to as the index. The terms of our sequence can be generated in a couple different ways. We could generate the terms randomly, so that there's no pattern or structure to our list of numbers. We could generate the terms recursively, so that the next term in the sequence is defined in terms of previous terms in the sequence. Or the context that we'll deal with mostly is cases where there's an explicit expression given for the nth term of the sequence. So there's some expression a sub n that tells us exactly how to determine the nth term of the sequence. And our goal in this case is going to be typically to investigate what I'll call the end behavior. So this is just what's happening to the sequence as the number of the index grows without bound. Sometimes the general term expression can be translated into a function of one real variable. In such cases, we call the sequence fourvable. This is definitely not a real term, but I made it up and I kind of like it, so I'm going to stick with it. And if a sequence is fourvable, then we can evaluate the limit by translating our sequence a sub n into a corresponding function f of x, and then just using what we know from Calc 1 to evaluate the resulting limit. Here's an example. We've got the sequence a sub n equals n squared plus 1 over 2n squared plus 3n plus 4. This sequence can easily be translated into a corresponding function of one variable, namely f of x equals x squared plus 1 over 2x squared plus 3x plus 4. And this function of one real variable is a standard function, rational function, type of function we're accustomed to dealing with from Calc 1. So if I'm interested in considering the limit as n grows without bound of the terms of my sequence, that will be equal to the limit as x grows without bound of the terms, of the values of this corresponding function. So I can plug in the name of that function. So I'll have the limit as x grows without bound of x squared plus 1 over 2x squared plus 3x plus 4. And now looking at this limit, I've got a few tools from Calc 1 that I can utilize to evaluate this limit. If you want, you can consider this as sort of a L'Hopital structure, since my numerator and my denominator are both growing without bound. As x grows without bound, you could similarly kind of neglect these not highest power terms and focus solely on the highest power terms in the numerator and denominator. Either way, when we evaluate this limit, we see that the value is exactly 1/2. Therefore, the limit of our original sequence as n grows without bound is also 1/2. There's a lot of cases, however, where our sequence is not fourvable. So there's some component or some feature of our sequence which doesn't allow us to translate it into a function of one real variable. In those cases, we can often evaluate the limit by just focusing on certain components of the sequence, figuring out what happens with those components, and then extending that knowledge back to our original sequence. So here's a case in point. We're looking at the sequence a sub n is given here. Our goal is ultimately to calculate the limit as n grows without bound of a sub n. And before I actually get to evaluating that limit, I want to just think about the structure of this sequence for a second. So first thing I notice is I've got two separate terms in my numerator over a single term in my denominator. So I can split this overall fraction into two separate fractions. Each numerator term over the same denominator term. Next, this -4 to the n cannot be translated into a function of one real variable, because if my exponent was a real value as opposed to an integer, then I can't have a base which is negative. But I do know that I could take this base of negative 4 and I could rewrite it as a product of negative 1 and 4. I'm not doing anything to my denominator quite yet. The second term here I'll just sort of copy and paste along for the ride for now. And now in this numerator I can actually apply this exponent to each of the terms in this product. So this numerator can be written as negative 1 to the n times 4 to the n. Got a little bit more work that I want to do to both of these fractions, but this separating that negative 1 to the n out of that numerator is going to be really helpful. The other thing I notice is that in both of these denominators I've got 8 to the n plus 1, and it's helpful maybe to rewrite that as 8 times 8 to the n. Remember, by rules of exponents, if I had this expression, I would add the exponents, and that would yield this 8 to the n plus 1. So this 8 here is actually just kind of an extra coefficient that I can bring out front if I feel like it. Let me do that in both fractions here. And then just a little bit more rearranging. Let me write this as, say, negative 1 to the n times 1/8 times 4 to the n over 8 to the n. Similarly, this second fraction I'll rewrite as 1/8 times 5 to the n over 8 to the n. Tiny bit more algebraic manipulations here. Here we go, just to clean things up a tiny bit. Let's see, both of these bases are to the nth power. So I could rewrite the base as one fraction. So this will give me 4/8 to the n. I can simplify that 4/8 and this will yield 1/2 to the n. Similarly, I could rewrite this as a single base of just 5/8 to the n. Okay, so I've taken my original sequence expression, just used properties of exponents and some algebra here, and I've rewritten it in terms of this. So now what I want to do, I've already noted that this first component cannot be translated into a function of one real variable, but the remainder of this expression can. Both of these exponential functions here can be rewritten in terms of a corresponding function of one real variable. So what I want to do is I actually want to consider the f of x that leaves this sort of trouble piece out. So let me jump down here and let me consider the function f of x equals 1/8 1/2 to the x plus 1/8 5/8 to the x. And now let me try to evaluate the limit of this function as x grows without bound. And now as I look at this function, as x grows without bound, each of these exponential terms, since they have a base which is less than 1, will approach 0. Think of it as fractional terms where my numerator, like in this case, 5 is getting bigger and bigger and bigger, but 8 is also, 5 to a power. 8 is also to a power and growing without bound, and so that denominator will dominate. And so each of those overall fractions will approach 0. So the value of this overall limit is 0. Okay, I'm not totally sure that this is my answer, because remember that this f of x isn't exactly the same as the a sub n that I was dealing with earlier. Well, actually, let's compare the two. So here's my original a sub n. Here's my f of x. The only difference between these is that this first term in my a sub n is going to alternate sign. It's going to be negative and then positive and then negative and then positive. But this second component of that first term is approaching 0. This second term here is approaching 0, as we just calculated a second ago. So the fact that this first term is going to alternate won't change the fact that this overall sequence will converge to 0. So based on this little work here with a kind of slightly modified f of x, I think I can conclude that my original limit will be 0.